So good evening, everybody. Hopefully you're not tired yet. I'll try to keep it short and interesting. Let's start with a quick preview of what's KVM. I guess most of you know what it is already. It's short for kernel-based virtual machine. It was merged like 4 years ago. One of the main interesting features of KVM when it was merged was the high reuse they did of kernel facilities. Instead of re-implementing everything like some other hypervisors do, they basically reused lots of the kernel, like the schedule system or the memory manager. And this also helped the pull request, the original one, to be pretty small. It was like about 10,000 source lines of code when it was pulled. The project succeeded pretty well. It went on to grow to the KVM we all know right now. It's pretty big, nice, and has strong corporate backing. Ubuntu, Red Hat, and lots of other big names. What it usually does to run the kernel side of KVM is pretty small. Basically what it does is mostly virtual CPU, memory management, and some very basic device emulations. Mostly small stuff like firmware chips and all those stuff. The real heavy work is being done in user space. And when I say user space, I mean QEMU KVM, which is a QEMU fork, which basically does KVM pretty well. QEMU itself, I guess most of you know it, if not as the KVM hypervisor, then as the awesome emulation platform it is, because it is pretty awesome. It's able to do quite a lot. It can emulate pretty much anything you can think about. To do that, it has to be pretty big. And as of August last year, it had 740,000 source lines of code, which is quite massive. The not so good part about it, that to do KVM, it needs very little. The amount of source lines of code that actually do KVM is pretty small in the entire project, which is called QEMU. So in July, in 2010, was it June? Ingo Molnar has sent a suggestion to the KVM mailing list. This is actually word by word of what he wrote, of the main paragraph. And he suggested to do basically 3 things. First was to take the KVM bits out of QEMU and put them into the kernel source tree under tools KVM. This suggestion made sense because it would mean that you now have the code base which is shared in the kernel, and it means that any further work on that source code would be done in just one tree. This leads us to point number 2, which says that whenever someone wants to do a KVM feature right now, he has to do it on 2 trees. One is the kernel source tree, and one is the QEMU tree. It means that when someone wants to do some sort of patch, he has to keep working parallel on 2 trees. Those 2 trees have different data structures, different headers, different coding style. It's confusing, it's annoying, and it means that the one who's doing that work has to know those 2 source trees pretty well. Instead of doing it this way, Ingo suggested that if we move it into one source tree, it means that when someone works on the features for that source tree, you'll have the same code base, you'll have same coding style, you have same headers, and you have same data structures. It means that it's just enough to know only one source tree. It will also mean, since the kernel side and the user space side would look very similar, it might encourage kernel hackers to actually work on the user space code, and user space hackers to work on the kernel side. It will add some more people who are working on the entire project, and not just like on half of it. That was the suggestion. That's how we wanted to see it be done. And he got hit by a big wall of reject. When the people who rejected it said that, well, first, there's no real benefit in moving it into the kernel tree. Right now, KVM lives in the QEMU tree. It receives quite a lot of contributions out of QEMU people who are not necessarily directly working on KVM. And they're pretty happy with it because they get more than enough support just being in the QEMU tree. The second point was that what they have now works, which is something we can't argue with because QEMU has been doing a great job as the hypervisor and KVM was moving along pretty well. And you can see right now that KVM is quite big, and it's done it with QEMU. So if it's working well, why touch that? I just leave it in QEMU. And the third point was there's no real merit in putting everything in one tree, because you can just write a whole bunch of scripts which will format your patch series nicely and send it as one series. You don't really have to put it in one source tree. It's not really worth it. So basically, once the huge discussion ended on the mailing list, he was pretty much told that, well, if you want to put something under tools KVM, then go ahead and write it yourself. So let's introduce the KVM tool. It was written from scratch. It's a very small code base, 15,000 lines of code currently, and it's pretty much stuck at this point for a while now. It's built to be easy, fast, and it's designed to be integrated into the Linux kernel itself. What this means is that the user space code will use data structures which are present in the kernel, such as, for example, the linked list or the red-black tree. It also means that it will use data structures within kernel headers directly, within internal data structures, without having to copy them over to different headers or redefine them in the user space. It can just directly use data structures. Another big feature of the KVM tool is that we always try to keep it simple. It means that if someone will run lkvm run, it will actually give him a guest which is pretty good to work on. It's not like when you run QEMU, you just see a big window pop up because it didn't specify 5 lines of options. You actually get a guest with a file system which is similar to what you see on the host. You'll get a working networking. You get a networking which is able to do requests, to do whatever you want to, without having to specify a whole bunch of different parameters. Although we didn't design it from day one, the code right now is architecturally free. It means that it's not tied to x86, it's not tied to anything in particular. We did do most of the developing on x86, but it's works not just on that. The code structure is actually very similar to what's being done in the kernel, when you have a virt KVM directory, which holds the common code, which runs on all architectures. And for each architecture, you have the arch something KVM code, which is architecturally specific, and it uses the common code under virt KVM. Well, quite recently, Matt Evans did a pretty good job porting the KVM tool into PowerPC. And as of this morning, it actually runs on a whole bunch of PowerPC platforms and not just experimental ones. If you do look at the patch series, you'll see that it's pretty short and pretty simple. It means that you didn't have to write thousands of lines of code to get everything to work. You just had to do 20 patches, small ones, and bam, you have PowerPC 64 support. Basically, the tool can be ported to any other architecture which KVM runs on. We'd be happy to see ports to either one of these if anyone feels like stepping up to the challenge. From what I've been told, x86 is the hard one, so this one is supposed to be much easier. Hopefully someone will do it. One of the another main things we insisted on when writing the tool is to keep the locking minimal. It means that the amount of places we take in release locks is very small. It's almost non-existent compared to the size of the project. There's no big kernel lock style of locks. It means that more than one thread can run in the hypervisor. It's currently a problem for, let's say, QEMU, which is unable to get more than one thread running inside the hypervisor due to the fact that they have to support the TCG, the tiny code generator, and they can't focus just on KVM. Since we don't have to do that, we can allow multiple threads to run inside the hypervisor at any given time. We have the same lock-in semantics as in kernel. This means that for kernel hackers who look at the code, it will look very familiar. They don't have to get into the big world of pthreads and how everything works over there. It's all wrapped nicely for them in the lock-in semantics they know from the kernel. It means it will be less scary for them to move to the user space side. We're currently working to integrate logdep into the user space tree, which is kind of surprising because logdep is mostly a kernel feature, and thinking about moving something like that to user space is pretty scary. But we can show how it will work, and we can demonstrate how doing something like this will allow us to use kernel facilities, such as logdep, to do things in user space. There's no reason why you shouldn't be able to use logdep or other kernel things to help you in user space. And logdep is a great mechanism, is something pretty good, which allows you to detect possible deadlocks and possible lock-in violations pretty easily. So there's really no reason why it shouldn't be used in user space as well. Now, BR locks is something which we conceptually loaned from the kernel. BR locks is basically a reader-writer lock, which is very cheap for readers and very expensive for writers. The idea to use these types of locks in very specific places, which we know that will be written rarely, if ever, and read quite often. I'll explain exactly how we use them in the next slide. Due to this pretty comfortable locking thing, we know that several people use this tool to develop on the real-time kernel. It allows them this great flexibility of knowing exactly, of having minimal locks and just knowing exactly what's going on in the code. Much easier to see what's going on when working on the real-time kernel and you have no lock-in inside the user space side. So this is an example of concepts we talked about before. I'll do a big background about port.io and memory mapped.io. Basically, port.io and memory mapped.io are operations which the hypervisor cannot serve inside the guest. The guest memory is divided into different chunks. One of them is the regular RAM we all know about. And there are chunks which represent devices. And devices, as we know, are mapped into the memory. So whenever a guest wants to talk to a device, he will access a little bit of memory which is assigned to the device. What will happen at that point is that the kernel, the hypervisor will understand that he can't help him with that request, with that read request or write request, and it will go back to user space to the KVM tool to serve that request. Now, when he comes back to us, we need to serve that request and return it back to him. So there are a couple of stages we have to do when we serve that request that are a good example of how we use kernel for our advantage. The first one is the augmented red-black tree. The augmented red-black tree is something which exists in the kernel tree, and it currently has just one user, the page attribute table. What this thing means, that structure is basically a red-black tree, which allows you to do modifications on it, to extend it beyond the simple red-black tree. And what we did with it was to take the simple red-black tree and turn it into an interval lookup tree, which lets us store intervals inside the tree. This means that whenever a guest exits to us, what we see is an address. So by having this lookup tree, we can quickly find which device owns that address. This lets us do a pretty fast translation from an address to a device. The next thing is a BR lock. Since this tree is written just when the machine starts, just when we're building a guest, or if we do hot plug, it also changes there, but these are very rare operations. So what we want to do in this case is to keep reads from the red-black tree pretty cheap, and writes to it can be expensive, because we don't mind, because it happens very rarely. So the way we implemented this concept here was to make BR lock suspend the guest. It's a bit scary, but what it means is that now reads can be lockless. It means we don't have to stop the get. It means that we don't have to do locking in the tree because we know it won't be modified since the machine is running. If we do want to do a write, we'll pause the machine. Once the machine is paused, there could be no I/O exits, no virtual CPUs running. It means that we can then safely modify the tree to do whatever we want. That's a good example of how we took a concept which was designed in the kernel to do kernel things and used it in user space. This way we have achieved a pretty fast lookup tree with no locking, without inventing anything new. We just took things which exist in the kernel and used them for our own purpose. We've considered using user space RCU. We did some basic work on getting a proof of concept working, but BR locks proved to be a more efficient solution, and it didn't require us pushing another user space library into the project. We might be interested in implementing it just as a proof of concept and keeping it inside the tree just to make it look more kernel-y. But we currently don't touch that at the moment, so if someone wants to play with user space RCU, just let me know. Now, regarding the BIOS, when you boot a virtualized Linux guest, you don't really need the BIOS. The kernel can do pretty much everything by its own, and the BIOS is pretty much optional. The BIOS implementation we have inside the KVM tool is also pretty optional. It's pretty tiny. It's less than 500 lines of code. We do only selected set of features. First of them is the interrupt 10, which is there so we could provide a graphical interface to the user. The second one is the E820 map, which is a memory map that the kernel will parse and know how its memory is designed. Now, basically, we really don't have to pass these two to the kernel. We can deal with both by just giving him the right kernel line command. But we did do that just because it's pretty nice interface. I mean, E820 is pretty solid. It's been with us for quite a while, and it's still doing its job pretty well. And it's much nicer doing it this way than doing it as kernel parameters. MP-table is also a pretty old spec. It's basically a firmware spec which was used quite a while ago to describe the construct of a machine. Basically, it defines the processor, it defines the memory layout, it defines the devices. And it's enough to get a working symmetrical multiprocessing machine. Right now, what most machines use is ACP, but we didn't really feel the need to use ACP at this point because MP-table pretty much provided everything we needed. So we just stay with that at the moment. Since we didn't use an external BIOS, it means we don't depend on any other project which will provide us BIOS. It means that the KVM tools is self-contained. It doesn't depend on third-party BIOS, and it does all the work by itself, but still keeping the code small and not bloated with lots of BIOS code. We are looking into optional integration with a third-party BIOS, when probably the leading candidate BIOS is a C BIOS, since it already supports booting from VirtIO devices. So we're looking into it, and we'll be happy to work on that if someone is interested in putting some work into that. As I mentioned, the guest can run a symmetrical multiprocessing machine. We support up to 254 processors in the guest. It's limited to 254 due to limitations in the kernel side of KVM. Since each APIC ID is limited to 8 bits, we only have 256 possible virtual CPUs. And one of those APICs is an I/O APIC, and one of them is reserved to broadcast, which lives at this weird limit of 254 CPUs. We use MP-table here, which coincidentally also allows us to define up to 256 virtual CPUs, which is a nice coincidence. So we kept MP-table because at this point it provides us everything we need, and there was no real reason to start working on ACP if we have everything we need to proceed. Now, what this thing does is allow us to do quite efficient debugging of things you only see in machines with a whole bunch of virtual CPUs or physical CPUs. I'll just demonstrate, because usually when people say that loading something like that is, let me do this. Usually when people say that, oh, support up to 200 virtual CPUs, just theoretical limit. Well, here you'll see that it works on my laptop, and you'll see that it gets to pretty high amount of virtual CPUs, and it does it pretty fast. I mean, it'll do it in like a minute. It'll take some time. What this means is that we can start working on problems which appear only on machines with a whole bunch of virtual CPUs, on simple machines like my laptop. It means I can start debugging issues which I would once need a huge server just on simple hardware like my laptop. A good example where we did this before is that a couple of months ago, there was a patch to change the RCU in the kernel to use K-threads instead of soft IRQs. And the first sign of trouble appeared when there was a reported regression of slowdown when you use 64 CPUs, and it was tested on a real hardware machine. Now, at that point, it was pretty hard to see what's going on because it's like a small slowdown, and it was hard to measure, and you didn't know what's going on. But when you tested with the KVM tool, you saw that if you try to boot a machine which has like 180 virtual CPUs, it would simply stall in the middle of the process. It would stall around 130 CPUs. Since you could then reproduce this behavior on every single laptop, it became pretty easy to bisect this bug and point it to a specific commit. It was pretty easy to find this bug, which you once needed the biggest server with 80 CPUs. You could now find this bug on a simple laptop. This means that it makes life for kernel hackers much easier, since they can now do things which they previously can't on their laptops. If we look here. We'll see that it actually runs 254 CPUs. Cool. Now, contrary to QEMU, we don't provide that many legacy devices which we support. We provide pretty much 4. First one is a real-time clock, because we thought it would be nice if the guest would know what's the real time once it starts up. Second one is the keyboard controller, which is basically supports keyboard and mouse. It's there to make booting into graphical interface easy, since if you don't have keyboard controller, you can't really type when you're working in graphical mode. We have the serial port, which was recently overhauled to support this fancy thing, which supports FIFO and whatever. This makes it pretty fast and very efficient. Why we want it pretty fast? Because it's currently the only method you can use to see early boot messages, like the one you saw when we booted that machine. That's why it's also like one of the interfaces which we feel is more important than its VirtIO counterpart, the VirtIO console, because it's much more useful right now. And the fourth and last one is the VESA, which is a pretty basic video controller, which there's nothing fancy going on over there, just a block of memory that the kernel draws on. We have, as I said, the minimal BIOS layer, which is also, you can consider as a legacy emulation. Everything else which has been done in the guest is para-virtualized, which means there's no legacy hardware emulation elsewhere in the code. So basically, when I say para-virt, I mean that we fully support the VirtIO spec, which includes a block device, network device, a random number generator, a console, a balloon, and a 9P device. 9P, if you don't know, it's a pretty old standard. There was this operating system, Plan 9 for Bell Labs, which had this concept of let's make everything in a file, which is currently partially true in the Linux world. On Plan 9, it was fully true. I mean, if you took their window, for example, if you took a graphical window, the graphical window would have a file that represents it somewhere. 9P is the communication transport which was used in that file system to communicate between different operating system devices. So basically, 9P is a pretty advanced file sharing protocol. We currently fully support VirtIO PCI, which means that it's possible to represent VirtIO devices as regular PCI devices. On the good side, it means that you don't need any extra configuration in the guest to get them to work, because the guest will automatically find PCI devices and work with them. On the bad side, it means that we need to add a small layer of PCI emulation to the code, which is not something you really want to do in a virtualized guest. We have patches to support VirtIO MMIO, which is this new shiny spec thing, which lets you to use VirtIO as platform devices. Well, the good part there is that you don't need to support anything legacy, such as PCI. The bad part there is that you have to manually specify where your devices are in the memory of the guest, which is not pretty at the moment. So we feel that it's not really usable by users at this point until it becomes more easy to use. We don't have the virtual support in the code at the moment. We have patches that demonstrate how it works. We're basically waiting until it stabilizes because it just got into the kernel. And we'll add it pretty soon once we start working on that. We support this thing called ifshmem, which is inter-VM shared memory. It's basically a block of memory which is shared between the host and a bunch of virtual machines. It's been developed for several years now, and there are several researchers which show how you can turn this shared memory to do pretty good stuff in a virtualized environment. One of them is, for example, a presentation which shows how you can use that shared memory as a pretty fast networking controller, which lets you achieve amazing speeds in networking, since you don't have to go through the entire stack of the guest and then go through the stack of the host. You can just use the shared memory to get out of the guest, and performance-wise, it's very, you can see it pretty easily how it will help. Since, as I said before, we implemented the Virteo PCI spec, it means we had to do a small PCI layer. Since initially we did the PCI layer, we saw that there are several performance problems, especially when you have to signal the devices, and devices have to signal you. It happened because we only implemented the legacy interrupt system, which means that every time the specific device wanted to signal something, it had to signal it across the entire device. What we did was implement support for MSIX, which is not so new standard anymore. It basically switches from using mechanical interrupts into a message-based interrupt, where what the guest needs to do to notify of something is, instead of raising the current or on a specific wire, it simply writes to an address of memory. This means that if you use MSIX, the guest has much more freedom in writing whatever he wants to that address. It basically lets him about 2,000 of different targets for each device, which means that you can efficiently signal exactly what's going on in the device. You don't have to interrupt the entire device. You can just interrupt a very specific queue within the device to do some job. Now, as I mentioned, we implement Virteo 9p. It's possible to use Virteo 9p to boot from a rootfs directory which exists on the host. This means you don't really need to work with images, since you can just give him a directory on the host and it will boot that directory. The benefits of it is that you don't need images. You waste much less space because you don't have all that extra garbage around. You don't have to guess how much space you'll need within that guest. And it means that it's pretty easy to access the guest file system from the host, so since it's just files on the host. So once we got that to work, we wondered, can we take this thing and just boot can we use it with any directory? And the first question was, can we use the host rootfs itself? Can we just boot a copy of the host itself? So we tried that, and we found that the answer is we can't. Because when we try to boot to the same file system of the host, we'll destroy the host pretty much, because the guest will overwrite whatever he wants. And it's pretty obvious that getting two kernels running on the same file system won't be smart. So we had to find an alternative way to do that, since we did want to get a guest which is very similar to what's going on inside the host. So we did it this way. We boot into an almost empty root directory, which has just basic layout, and it has symbolic links to key directories inside the guest. What we did was then mount the host into a directory inside the guest as read-only, and ported those symbolic links into the host. Directories like bin, lib, and the friends. This means that when you boot into that special guest, you have an environment which is very similar to what you have in the host. You can run exactly the same programs you have in the host. You can access exactly the same files you have in the host. It makes testing of things you've done on the host very simple, since you just boot into it and you have an exact copy. We did want to integrate it with something that's called overlay FS, which is, some of you probably know it, from Fuse. Fuse already does that. It's basically a file system which lets you place another copy and write file system on top of it. So if you change the file system somehow, it got saved into the copy and write thing. The problem there is that overlay FS can't seem to get merged into the kernel. While we try to push it and we encourage it, it can't find its way into the kernel. We're very hopeful that it will soon get merged, and then we will be happy to add overlay FS support, which would make it easy for us to remove this, what you might call a hack, out of the code and just use yet another kernel interface for our tool. So what's so special about this custom rootfs thing? It means that, as I mentioned, that it's pretty easy to share data and programs between guest and host. Because if you just run whatever's on the rootfs of your host, you get full access to the host. This means we can do sandboxing pretty easily, since you can run any program which exists on the host, but it will run inside that guest. It means that if you'd like to test something dangerous you did, or you'd like to test a kernel patch you did, and you can reproduce it in user space, you no longer have to patch your own physical machine, reboot, run your test, see if it went okay or went bad, and then just do that again. Instead, you can just do this simple sandboxing thing. It basically makes life of testing and reproducing bugs and doing a whole bunch of things much easier, since you're sharing the same root directory as the host, and yet you run in a sandbox environment inside KVM, which is pretty secure. Another thing which we provide inside the custom rootfs is user mode networking. User mode networking is basically a proxy, is a TCP IP proxy between the guest file system to the host file system. While it's not very efficient, it's also just a user space solution. This means we don't need any special permissions to run that, because it just works in user space. It's just a simple TCP proxy. But what it also means is once you boot into the custom rootfs, you have a working networking. You just have a network that works without having to do DHCP, without having to configure it, without having to configure bridges on your host. It just works magically out of the box. Zero config mode means that if you don't really sure what you're doing, if you just launch LKVM run, as I mentioned before, you'll get everything working out of the box. You'll not need to figure out what's going on if you don't want to dig into the spec. Launching it this way will give you a sandboxed root shell inside the KVM guest. It's pretty easy, you have to admit. One of the nice things we did with that was automatic bisection of kernel bugs. Since we can now sandbox things inside the KVM guest, it makes testing pretty easy, since all you need to do to test is launch a virtual machine. So we loaned a tool called Trinity from Dave Jones. Trinity is basically a pretty smart and advanced syscall fuzzer. It has data about different syscalls, and it knows which parameters they might expect. We combined it with git bisect run, which lets us use a script to determine the result of a test. And getting all of this to work together, we basically can now find bugs inside the guest since a sandbox. We can reproduce those bugs once we see how it happens, and we can use git bisect run to quickly find the commit which caused that bug. Another option we thought about would be hardware device bisection. I mean, everybody got this thing when they installed a new kernel version, and the graphics card broke, or the network card broke. Now, using this, you can assign that device to the guest and bisect that thing inside the guest. It means you don't have to restart your host to try to see if it's working now or it's not working now. You can do that inside the guest. Now, you're probably asking yourself, is it really working? So this is a list of things from the last 2 or 3 months, LKML threads, which bugs which were found by Trinity and the KVM tool. If you'd like to look at that, please go ahead. It's doing a pretty amazing job, and it's doing it almost on its own. I don't do much over there. It just automatically finds them, and I'll just do the mail thing. Now, if you do want to debug it, It basically supports a basic interface for getting into it and doing whatever you want. First, you can attach a JDB debugger into the kernel and debug it just like it was a simple process using KGDB. You can set the sysrec to the guest, which will make it dump a whole bunch of useful data. If you don't want to get into the guest, you can use KVM debug, which lets you print the status of memory and CPU registers without touching the guest. Or if you really want to, since guest memory is a simple memory map inside the hypervisor, you can access guest memory directly and just poke around in bytes over there and do whatever you want. The implementation for block device we have is a simple implementation for virtual block. The design there is asynchronous, using native vector asynchronous I/O, which is as fast as it gets on Linux without going into the kernel. We use the entire interface that the kernel provides us, and we do it we just as efficient as it gets. We don't have locking inside the code, except one lock, which is used to demultiplex, putting all the data back into the virtual device, which is like 2 assignments and 2 increments. The idea here was to make the device stand alone. It's separate from the rest of the code. It just uses the memory of the guest, and it's working as efficiently as it gets, using things that Linux provides to the user space. The disk formats we support are simple raw disk image, which you can boot as copy on write using mmap, which is yet another Linux interface which you didn't feel the need to re-implement. Same goes with block devices. You can boot your the block device, any block device you want, and you can use copy on write as well. It means that you can boot your host partition in copy on write mode, which is very similar to the custom rootfs thing, but it means here that if you want to do that, you need root permissions to actually access the block device. We have experimental QCOW and QCOW2 support. It's there just to make lives for people much easier, since we know a lot of people already have those images, so why not let them use them easily? Networking, there are 2 basic options. One is TAP, which is the regular TAP network. It creates a TAP device on the host. We can use vhostnet to speed things up. It's pretty standard. It's the TAP networking you all know, probably. And the user mode IP, which I talked before, which is the TCP IP proxy. By using that, we don't need any privileges like we need in TAP. It gets configured automatically by the kernel. We use the DHCP client located inside the kernel to configure the IP of the guest. It means you don't need any extra tools on your user space guest or anything like that. Everything is getting done in the kernel. We fully reuse whatever the kernel already gives us. User space interface is very similar to what you know from Git and perf. We actually stole the code from them, so it's very similar. If you want to automate everything and keep working on, you feel like you're home, because it's pretty much what you see in Git and perf. We provide 2 textual guest console options. One is virt.io, which is pretty fast, but doesn't let you see early boot messages. And one is the serial console, which you saw before, which is a bit slower, but you do get to see early boot messages. We also provide 2 graphical console options. First one is SDL, and second one is VNC, which is pretty straightforward. We'll just let you do them if you want to start an X server and get nice graphics and everything. Now, things we want to do in the future. First is virt.io, which Paolo talked about. It's the latest hot thing in virt.io, and we really want to get that into our code as well. We just need to rediscuss the spec at some point, since none of us really knows SCSI, which is a bit problematic. Second thing is ACP. While we don't strictly need it at the moment, it will open the door to getting hot plug to work, which might be interesting for us. Third is Mac VTAP, which is like vhostnet's brother, which we also like to get to work. It should improve performance significantly, but it also means you have to deal with something which is poorly documented, which is probably the reason why it didn't go in yet, because the documentation is pretty lacking. Fourth thing is int12 support, which is a BIOS facility for reading directly from hard disks. If we implement this, it means we can start booting directly from images. Since currently we don't boot directly from it, we just skip the BIOS part. We inject the kernel code into the memory and just boot from it directly. If we do it using int12, it means we can go through the standard booting process. So when you see your BIOS, you'll see grub starting, and then you'll start your Linux, and then you'll do the complete boot. It can be done by means of integrating with an external BIOS, like CBIOS, which shouldn't be a problem. You just need some work and try to figure out how you get the machine started well and how you get CBIOS to recognize that we have a bit non-x86. Well, we have an hacky x86 implementation, so we'll need to improve on that once we add an external BIOS, which will not accept that thing. We'd like to get the QXL private controller, since, as I said, we implement a pretty basic VESA. So if you launch an X server, it'll be slow, terribly slow. It's working everything, but don't expect NES graphics and don't expect to play Quake or something like that. We'd like to see perf integration. So since used a lot by kernel hackers, and if we integrate it with perf, we'll let kernel hackers see results of things which run inside the guest on the host. It means that they could do their own testing inside the sandbox KVM guest without having to go into it. They could receive everything on the host. We'd like to do love migration, which is something we currently don't support. It will require some work, but we think it's a worthy feature to have. We'd like to port it to more architectures. We currently do x86 and PowerPC. And there are some initial work to port it to ARM, but we'd be happy if we could get some help on that because we're mostly x86 guys. If someone knows it and wants to help, please do. We also like to support non-Linux guests. We would be interested in booting Windows, but we're not even close there yet. If you want to boot Windows, it means we have to start implementing another big bunch of devices which are legacy and which we don't want to implement. But it's probably worth it just to see a different operating system booting, not just Linux. And here are some links if you're interested in joining in. The first one is the GitHub where we hide our code. Second is the Git tree itself. And we're using the standard KVM kernel mailing list to communicate. So if you already work on KVM, you probably saw us already. And if you don't, just subscribe to that kernel mailing list and just ask away if you want to communicate with us or just look at our patches or whatever. That's all I think. Yep. Thank you very much. Yeah. Sorry. Mm-hmm.
I think it's the QEMU part of the CPU emulation where it actually adds support for doing
Mm-hmm.
and with the tool design supporting QEMU.
Most of the problem with the QEMU was that you didn't pass the VMX flag into the guest. QEMU solved that problem just by passing it into the guest. Here it just works out of the box since we passed every flag you have on your CPU to the guest. So it just works out of the box.